let's continue with animation. I'm excited to like make the example that was already cool last time with the ball going up and down. Let's continue with that. Let's make it fancier. All right, so let's go back to that code actually. I'll have to do a few things. New folder for today. This is lecture 25, and I'll copy in the one that we did last time. We called it bounce, right? And I will call it bounce copy, I guess, so that we know we didn't just make it. There we go, and I'm going to open it in idle. There's a nice little right-click menu for me, at least, that does that. Okay, so here's the code. Remember what we were doing last time, all this fun stuff? Click to run module. We drew our little bounding rectangle with a call to our draw rectangle function. We picked some starting places for our turtle who became the ball, and then he's going up and down, and each time he's being moved, it's happening in this draw frame. So really, this is like a forever loop, while true, until the end of time. Draw a new frame, which is going to take care to move the turtle, change his Y position based on his offset, either going up a little bit, nudge him up a little bit, or nudge him down a little bit, and like worry about hitting the walls as well. And so we get nice motion based on that, and it's beautiful. Okay, so hopefully it's coming back to us. But that's kind of what we were doing, and like it was all down here essentially. That was driving the animation, right? Just that loop. Repeatedly draw a new frame. Keep going, and somehow that produced animation for us. So like let's talk about that, because that's a little confusing. Like, why does that do it for us, right? Because I told you about films, right? You have to, like, if you want to make a movie or something, you have to very tightly control the frames that you're showing, don't you? You have to, like, right, the first frame is this one, show it for 1/24th of a second. Then the next frame is this one, show it for 1/24th of a second. And the frame after that's that one, show it for 1/24th of a second. We're not really putting time anywhere, are we? We're not saying 1/24th anywhere. We're not doing any of that. So technically, you might imagine, it's like a philosophical question, I guess, if the program just kept drawing frames forever as fast as it could, because we're not telling it to stop or slow down, are we? If it was doing that as fast as it could, like, wouldn't that mean that it would just keep trying to draw a frame over the one it kept trying to draw before? Like, it would never actually draw anything. It's like, keep trying so fast. So it doesn't actually do that for some reason. Like, wouldn't it show frames so fast that you never see anything? Like, it's always like clearing, redrawing. But that's not what's happening. So there's something secretly going on that's making the program wait for a split second and is producing animation. There's something that's making it wait, even though we're not telling it to. Okay. The secret is that it takes a while to do some computation inside of a computer. Like, we're telling it to add some numbers. Like up here in draw frame doesn't run in the blink of an eye. Well, it kind of does for humans. But as far as the computer is concerned, it takes concrete amounts of time to do an addition inside of a computer and to shove the answer into a variable. Like, that takes a little split second for the computer to do that. And like the turtle.goto is where it's like actually drawing the screen in a new way, like changing what the pictures are. And in the turtle window, like that takes the most time, that turtle.goto. And just like doing that and adding up the amount of time it takes to do the additions, to do the less than check inside of a computer, inside of the processor, and like to do the .goto, like do whatever it takes to like change the, like redraw the window here, clear it out, re-put in like wherever the turtle needs to be now. All that stuff takes up time, even though we're not telling it to stop. It's just like, it assumes we want to complete all this, and we do. So it's going to run all this code to completion every time we call draw frame, and that will take up a little split second, right? We're not really having much control over how many split seconds, but that's what's going on, okay? So there's a tiny bit of time for each draw frame call, and that's going to be how long that previous draw frame was, or that previous frame was shown on the screen, however long it takes to do the new one, to call it the next time, okay? So that kind of makes sense. So that's what's going to give us animation for a split second in between these calls, because turtle.goto is what changes the picture for us, right? It's doing some additions and comparisons, and then doing another goto call. So in between those calls to goto, we have this screen in a still image, essentially. Like we haven't touched it for a split second. And that is why it is going to wait and show us stuff, right? That's going to produce our animation for us. If you wanted more control over your frame rate, how fast the frames are being drawn, you can use a function in the time library. It's called time.sleep. It tells the program to go to sleep for a little bit, which is kind of cute. So if I search for Python time, the time library gives us that control, and so we can tell it to sleep. Where's that? There it is. So sleep, you give it a number of seconds, and it will just pause the program, make it go to sleep for a certain number of seconds. Okay, so that's what we can do here. And so if you wanted choppiness, you could have it sleep for 1.5 seconds somewhere in draw frame. Okay, we got to import time to get there. Okay, so let's try that. I'll import the time library up here. And then somewhere in between these calls, I'll add like time.sleep. So like I redraw the turtle and then like make sure to wait there for a little while. Time.sleep, I don't know, like a tenth of a second, let's say. So like it's 10 frames per second at most now. It's going to be less because this stuff we know takes a little bit of time. So we're going to see the frame rate now because like humans can notice tenth of a second. I'm stopping it now. I'm concretely stopping it. And you can see it be choppy, right? I'm telling it to wait exactly that amount of time before you give up and finish the function. Just wait right here. Tell the program to go to sleep right after drawing, and that's going to produce this image. And that may make more sense to us now. Like we're actually telling it to wait. That's kind of like a frame rate at that point. Okay. Whee! But it's very choppy. If you wanted it to fix it, and if you wanted to keep this frame rate, you'd have to make the ball move a lot faster, right, with the offset, like maybe -10 or something. Have to move around all over the place. But does that kind of make sense? You can control it if you wanted to. You could like set a little timer and figure out how fast your frame rate is as well. But now we're stopping at every tenth of a second. And like that is now stop motion animation, I guess. I don't know. Does that make sense? Any questions about that? So you can have that kind of control if you want it. The turtle library doesn't really make it super easy, but you can do it. But we were just getting a frame rate based on how fast it took Python to run this code, is all I'm trying to say. Okay, so that's the secret there. That's what's going on. And yeah, there's more to it. So the next thing that I want to do is mix up what we just did here. Let's make the ball actually bounce, not at a constant rate, but like let's model the Earth and like make the ball bounce with gravity and eventually stop because it's not, every time it bounces, it's not a perfectly elastic collision, right? There's friction. So let's model all that inside of our simulation. It'll be very cool. It's like we're going to make the ball bounce, and it's going to like start slowly but speed up as it gets closer to the bottom, right? Because that's what balls do in real life. And then it won't bounce as high. Woo! And so like there's a motion to it, okay? And so that's what we want. We would like to model gravity inside of our program now. I'll show you how easy it is, actually. It's really not bad. It will help, though, if you have taken a physics class. So I'm going to use some physics terms in a second. But just like as humans, as people who live on Earth, you know what it's like to drop a ball, right? If you drop a ball and you start a timer, like you wait like half a second or something, and you look at the ball right here, what's its speed right there? It's pretty slow because you dropped it from motionlessness, right? The ball needs to take time to be sped up by the gravity, okay? And then if you wait a little bit longer, the same amount of time, it's moved a little bit more. If you wait a little bit longer, the same amount of time because it's being pulled down by gravity. So it's going faster the closer it gets to the ground. Does that make sense? That's what balls do, okay? At least if there's no air resistance. So by the time you get down to the ground, like you are as fast as possible. You're going super, super fast down right before you hit the ground. The ball is, at least. Because like that's as fast as gravity's been pulling you down. It's been pulling you down faster, making you faster and faster until you hit the ground, and then it all resets, essentially. Okay? So we need to represent that inside of a program if we'd like to make the ball bounce with gravity. Okay? That's our goal. So I have to teach you physics for a second, I'm sorry. Hopefully you've seen a little bit of physics before in your life, but we need to learn about kinematics equations, okay? How do things move? So right now, what our ball does is it moves with a constant velocity. I think I need to make a new folder, not a new folder, a new file with all this. And I'll undo what I did with the choppiness. I'll make a new file. And I'll save it, and I'll call it Bounce with Gravity. That'll be super cool. So let's get rid of the time.sleep. Let's change the offset back to something normal, like I think it was -2, right? And then, so I don't need the import time, but I'll keep it there for fun. So now it should be back to normal. So if we were to use physics terms right now, this ball is moving with a constant velocity, okay? That's what it's doing. It's moving with a constant velocity, and it is staying the same speed always, which means it has a, it's not accelerating. It has a 0 acceleration, okay? We've heard those terms before. So yeah, our ball right now is moving with a constant velocity. And remember that what is velocity? It's the change in where you move to. It's the change in your position. Velocity, that is the change, or delta, right? Delta position. That's what that is. That's not what happens in real life. The ball should be speeding up on the way down. And now the question is, like, how fast in real life does a ball speed up? How fast does it change its speed as time goes on and it gets closer to the ground? And that is, right, the real physics term that we should be asking is, what is the acceleration of the ball? Okay, because the acceleration is your change in velocity over time. Acceleration is delta velocity. And that, on Earth at least, close to, I guess, ground level, sea level, is 9.8 meters per second squared downwards, right? That's that. And if we haven't seen acceleration units before, this might be a little weird, the squaringness, but like what it means is, like, remember that like acceleration is your change in velocity every time. So if this is just meters per second because it's squared. So you say that the ball is speeding up by 9.8 meters per second. That's a speed, right? Increasing in speed every second. Second per second. That's why it's second squared. That's what's going on. That's what the ball is being pulled down by if we dropped a real one on Earth. All right. So 9.8 meters per second squared. If I can draw an M. Increasing in speed by 9.8 meters per second every second. Okay. That's what's happening. And if we want to model that inside of our program, we have to keep track of acceleration and velocity. Okay? So essentially every time a frame happens, we need to let whatever our acceleration constant is affect our velocity. So like at the beginning of time you drop the ball, its velocity, let's use variables now. We'll need these. Its velocity starts at 0, right? It's just it's at a standstill. If it was in space, it would move. So velocity is 0 at the start, but acceleration, that is always going to be -9.8 because it's downwards, right? The negative y direction. So essentially every frame, if we want to model our program like this, every frame we want to have the acceleration affect the velocity. Okay, 0 seconds, 0 velocity. But 1 second later, right? 1 second later, it should be sped up, right? The ball should be moving at -9.8 meters per second. Does that make sense? And then another second later, you have it affect it, then it should be moving at -19.6 meters per second. Does that make sense? That's what's going on. It's wait another second, it's moved more because it's speeding up. Now the ball is way down here in the same amount of time. So the acceleration needs to affect the velocity every frame or every second, depending on however you want to model this thing. Okay, so we're just going to use a variable, right? Acceleration, and have it change our velocity. We already have the velocity variable, don't we? That's this one. Which variable affected the speed of the turtle? I change it and it affects the speed. It was the offset. That's the offset in the y direction each frame. That's your velocity. Does that make sense? It was constant, so it was moving at the same amount, same units every frame. We're going to have this be affected now by our velocity. All right, so that's the secret. That's what we're going to do. And yeah, it's going to turn out to be very simple. All right, I'm just going to change the names of these variables right now, though. So let's see. This can't be called turtle offset anymore because we know it's being used for speed purposes. It's turtle velocity, really. And it's sign, so down, negative means it's moving down, positive means it's moving up. So that's perfect for us. So we're going to call not turtle offset, we're going to call it turtle velocity. Okay, so turtle velocity. And the second you drop the ball, it's from a standstill. So the initial velocity of our ball needs to be 0 now. Okay, the initial velocity of the ball is 0. So Now, instead of saying turtle offset everywhere, I'm going to say turtle velocity. Velocity, velocity. Let me know if I missed one. I think that was all of them, as far as I know. And now, okay, we're back to that. But now we also need turtle acceleration. All right, turtle acceleration, which will be affecting the velocity. So, turtle acceleration, like negative 9.8 or something. We'll figure this out. Okay, so this isn't though per second, because we're affecting the speed every frame, right? That's what draw frame is going to do. We're going to change it every frame. So really, the units for our acceleration are not going to be meters per second squared. It's going to be units for this acceleration variable. They're going to be, because we're going to affect it every frame, the velocity every frame. It's really, well, units in turtle land per frame squared. So it's going to speed up by a certain amount every frame, by this much every frame. So units per frame, essentially. And so this is way too big, honestly. If you're affecting it every split second, I'll make it like a negative 0.5 or something small. I think that'll be better. Or let's do negative 1 or something. I don't know. We'll make it smaller later. But that's the setup. Those are my two variables now, velocity and acceleration. And all that I want to do now is every frame, I want to let the acceleration affect the velocity. So, all right, the velocity is whatever it is right now. Have it be affected by acceleration. Just like add it in. That's all you need to do. Okay. So back here, it's really just going to be one line. It's going to be, all right, we are going to mess with the turtle's position. That's based on the change in velocity. Or sorry, the position changes based on the velocity. That's still there, right? That's still fine. And let's see what else. But before that, we want to have the velocity affected by acceleration. So I'll say turtle velocity equals whatever it is plus turtle acceleration. And that's really the only new line other than this one up here. Isn't that crazy? So what we're doing is like the acceleration needs to affect the velocity. That's how the world works. Like at the initial time, velocity was 0, but it's being moved down, right? It's being changed by negative 1 every frame. So it's going to be moved down faster and faster. It's going to move faster and faster because the velocity gets bigger and bigger in the negative direction, and it will affect the actual position of the turtle based on this turtle y variable. Okay, so that's a lot of words, I know, but here, let's watch it. Look at it. I think it's moving a little, maybe too fast. I don't know. We can change what our acceleration is. But do you see how it is kind of speeding up as it gets close to the bottom? And it's also just by a quirk of the way that we programmed it. It will eventually stop and like dribble. It's really cute. So I'll have to explain that too. But like, we added what? One line and one extra variable? And we got gravity? That's pretty cool. Okay, are there any questions about that for now? I have more diagrams to do though. I think that's kind of magical. And you can change, like, all right, we were on the moon or something, let's like go back to Earth or something, make the acceleration bigger, like we're on a bigger planet now. It's pulling us down faster, pulling us down harder, so it's speeding up as it goes down, which is kind of neat. And then, all right, let's make it negative 9.8, I don't know. Let's see how fast that goes. It's just going to affect it in a different way. On Jupiter or something. But I don't know, it's up to you. You can play around with it. But it's got to be in the negative direction first, because it needs to pull you down. Or, sorry, the acceleration never changes, excuse me. It's got to be negative. It's always pulling us down, never up. So that's, all right, that's like we're on the moon now, 0.5. It's bouncing in that way. But it is speeding up, and we can print this out. All right, so let's add to this code. Let's be like, all right, let's like print our current velocity, because it's going to change over time. Print turtle velocity. And that will appear, oops, that will appear over here in the REPL. So look at it go. See how it's speeding up, and now it's slowing down also as it's going upwards, because like it has positive velocity and it's being changed, right? It's being changed. That's pretty neat. For some reason, it wasn't happy about printing that out so long. But down here, you see like it's starting at 0, it's getting more and more negative, speeding up, and then it's being slowed down as it's going upwards, right? Because the velocity is going to be positive to move it upwards. It's being slowed down because gravity keeps pulling it down. And so that'll eventually bring it back down to the bottom there, all right? So that's pretty fun. And just by a quirk of the way that we did things, it will eventually stop as well, which is kind of neat. All right, so yeah. Are there any questions about the code so far? It may seem a little magical still, all right, but we'll get that. So the reason it stops right now, I'll stop printing this. It looks like the maximum speed it ever hit was negative. Oh wait, I think I'll have to like start at the top here. What's the maximum speed in the downwards direction it ever hits? Bam. It looks like it was negative 19, but then it shot off a little less. And that's what's going to eventually bring it down. All right, let's see here. How can I draw that? So yeah, here's kind of what happened. What's that? Can you say that again? I didn't quite understand. What about the code is confusing? What can I explain? No, yeah, it's no, if you can formulate a question. Yeah, take your time. So if you can think of a question, please ask it, but I will try to draw what's going on right now in another way. So like at the very beginning of time, our velocity was 0. And then our acceleration, like at the first, it was 0.5, but I made it -1 at the start, right? And each frame, like the velocity was 0, we didn't draw the ball, it wasn't moving. But then it became like -1 the next frame. And so the ball did become affected by a speed. It has a speed now, it moved down a little bit. And then the next frame, we made it -2, which letting the position be affected by that new -2 velocity is going to move down -2 that frame, -2 units. And you keep on having the acceleration affect the velocity, it'll move down more and more and more each time. That's kind of what's going on there. And the reason why it didn't bounce up as high and it eventually stopped is just because of the way that we kind of checked for wall hitting, essentially. Because sometimes it never actually hit the exact bottom, I don't think. So like what we did, remember when we coded up how it bounces off the bottom? It's like sometimes the ball might try to move here and we just like move it up to here or something, and then send it back off. But it really was down here, and just like that moving it up and taking one frame to do that bouncing has the acceleration affect it in a slightly less way, kind of. That's what's going on. So you saw that it was it came down to -19, but just due to the way that we check for bouncing and handle bouncing, it didn't shoot off at -19 like it probably should have in real life, right? If there was no friction. And so that's going to allow it to lose some energy. We'll let it lose some energy and eventually stop. So I need to stop it from printing because it stops. I'll comment out that line so that doesn't happen anymore. But it loses, just due to the way we did it, it loses half a unit of velocity every time it bounces off. And so it's going closer and closer to the ground. So that's the secret. That's why that's doing that, just due to the way that we're doing the bouncing logic. Let's see what else. If you wanted to pretend like there was no friction, you were in like space or something, but you still had gravity somehow, you could just shoot it back off when it hit the ground. You could say, see, it eventually stopped. You could tell it to not do that. You could tell it, all right, if I hit the bottom wall, that's this code, right? If I hit the bottom wall, I would like this to be a perfectly elastic collision, if you've heard of that from physics. So we were doing it like this, just like changing the velocity to be -1. So like that's fine. But if we want it to bounce off with the same speed, we can just like hard code it. Turtle velocity, bounce off with exactly, what was it, positive 19.0 upward speed. And then it'll keep on being affected. So that will create a perfectly elastic collision by hard coding new velocity. All right, so it's a lot of physics terms today, but that will lead to, like, this will force it to shoot back off with the same speed it had coming down. And so it will always just like bounce right back up to the tippy top and it will never stop now. Okay? You can go back to how it was with this code and get rid of this if you would like it to eventually stop, just thanks to a quirk in the way we handle the bouncing. But yeah, I think that's all that I wanted to say. It's a lot of fun ideas, but what did we have to change to get this, to get gravity? It's amazing, right? We just had to model what happens in real life. We had to add acceleration variable and add one line in draw frame. We got suddenly bouncing with gravity. I love that so much. All right. Yeah, any questions about that? This will be some good code to study. I'll give it to you, of course, as usual. That is, I think, the main example of the day. So exciting. So yeah, it's never going to stop now. All right. The last thing that I want to do today, it'll take some time. I would like to bounce in two directions. Have we all seen this Office episode? I'm going to show it to you in a second. A little clip. They'll ban my YouTube channel though if I show it to us and also record this, because this eventually goes on YouTube now. All right, I get to keep my YouTube channel. But what we're going to do is change what we had. We had code that did this, that had it bounce straight up and down, y direction only. We have to suddenly now do something a little more complicated. We'll make the turtle a box instead of a circle, of course. But we got to give it some horizontal direction as well, right? Move off diagonally and like bounce off the walls in the normal way that they should be bouncing. And eventually, maybe, it will hit a corner. I don't know. If you wait long enough. Boop. Maybe there. I don't know. But that's going to be what we code. Okay? So we're going to have to add a new axis to what we're doing. So we're not going to code this up this time. We're just going to like plan, because there's a lot of thought that needs to take place here. We're going to plan what we need to do, and we'll have to discover like what is it going to take what we had and make diagonal movement instead of just straight up and down movement, right? So here's our game plan at a high level, and we'll start breaking it down, all right? So we'll code this up next time, next programming lecture, but try it yourself if you can before then. So I'll give you all the pieces you need, but the game plan again will be draw our little bounding square, because that's where all the scene is going to take place. We'll keep that in, right? We already have that code. We'll keep on using that. And then we're going to make a square in a random location within the bounds, all right? So we can make the turtle the square. That's easy. Like, that's fine. And then we have to give it a random direction. We have to somehow represent the fact, like, here's the turtle. Its center is there. Let's give it a random direction that way. Like, how do you represent that idea of moving that way, exactly that way, inside of a computer? We're going to have to talk about that. We'll have to figure that out. And, all right, once we have done that somehow, figured out how to move sideways or how to represent sideways movement, the idea of it, we have to, well, forever, again, just try to move in your current direction, right? Try to move in your direction if you can. It's like that'll bring it here or something. That'll bring the square here, and like keep on moving in that direction as long as you can until you hit a wall, right? Because we have to deal with walls still. And like that's pretty much the same as your bouncing ball, right? It's like we were affecting the Y, but we'll also need to affect the X as well. We'll have to figure out how to represent the directions, but like once we have that, it's just like move in that direction like we were doing with the ball. That's fine. Just not straight up and down anymore. And then if we do hit a wall, we need to bounce off. And that bouncing is not going to change our direction from down to up or anything. It's going to change it from this way sideways to like this way sideways. Yeah. We have to somehow use our old direction, know which wall we hit, and then like create the bounce in the opposite direction in the correct kind of new diagonal way. You see that? And then just, all right, keep on playing that game. Keep on moving in that new direction until you hit a wall. And then bounce off and change your direction. Now it's got to be that way, right? We're going to have to represent that. We're going to have to figure that out. Okay? But at a high level, does the code kind of make sense? If you knew how to do all this inside of the code, like this is what you need to program. Forever, keep on moving by a little nudge in that direction, bounce off the wall, which is going to involve changing your direction somehow. All right. So I guess the first main thing to tackle is how in the world do we represent a direction that is sideways and like weird? Like how do we differentiate that direction from that direction from that direction? All those things. Well, let's figure that out. Let's zoom in. Zoom into the idea that we need here. Okay. So first of all, we can make the turtle the square. That's easy. All right. Then he'll have coordinates. Let me draw a picture again. Once the turtle's the square, we can move him around with the dot go to like we were doing with the ball. That's fine. That's easy. And then the next piece of the puzzle, and then we also know it's very easy to set his coordinates to a random thing, like between negative 200, positive 200 for the x and the y. And then he's always moving relative to his center. Like, that's fine. But now we need to represent directions. All right. We can use, like, he's got coordinates. We need a direction now. Okay. How were we doing direction before? We were doing it with a number, right? A number to mean how much the y is going to change, right? I hope it kind of makes sense that, all right, we had one offset to be the y direction. We're just going to need another offset to have some x direction as well for two-dimensional movement. That's what we're going to need now, okay? Because every time you move, let's see, how do I want to do this? Every kind of movement, like I want the turtle to move in that exact way, that box to move in that exact way. You can break that down in two, right? If I want him to go from here to, like with that direction, like move him straight to right there, exactly there. You can break down this movement from here to here in terms of the following. In terms of what is moving diagonally exactly like that, but moving a little bit in the x direction and moving a little bit in the y direction. There's a right triangle there. You see that? So you can break it down in that way, and then that makes it easier. Like move a little bit in the x direction, that much, that tiny amount, and then also move a little bit in the y direction, go up that little bit. And that will produce, if you do both, sideways movement. You see that? That's going to be the trick. All right? And then, like, we just have to, like, encode offsets here. Like that amount of offsetting. So, for example, let's see here. You know, just move by a little bit in the x and a little bit in the y. And every possible direction you could ever want has some xy offset. Let me try and draw some. So, like, moving straight up is, like, don't change the x. 0 offset for the x, but y is positive. Down is 0 offset for the x, y is negative. This is a little bit right, so positive x, positive y. A little bit right, a little bit up. This one is positive x, move to the right, 0 y, don't move up or down at all. Right? And then this one is going to be what? Negative in the x, negative in the y, positive in the x. Go down and then also right. Do you see how there's always going to be an associated a little bit of offsets to get anywhere you want? That'll be it. Okay? So let's say, for example, that we chose, I'll draw a picture now, we chose that, all right, our delta x is going to be 3, and then our delta y is going to be, let's say, 1 or something. All right? It's kind of like this one. Move a little bit more in the x than you do in the y, but still upwards and to the right. All right? So how would we program this if we knew that those were our offsets and that was our direction, representing kind of that kind of movement? What would we do deep down? Well, we've got our square in some place. Let's say that the coordinates are 1, 1. And then we have our little xy offset that's going to take us new places. We have our diagonal movement based on these guys. And, all right, if we start at 1, 1, and we're going to draw the next frame, well, we need to change the x and the y by this amount. Change the x by 3 and the y by 2, which is going to mean, all right, go positive 3 in the x direction, plus 3 over there, and then also go up by 1. And that will bring our square to be right there, which now is, it's like, all right, the old x was 1, plus 3 is 4. The old y was 1, plus 1 is 2. Now it's at the coordinates 4, 2. And that's diagonal. That's pretty cool, isn't that? So we got this movement just for free. And let me see here. Let me redraw that. Start at 1, 1, went to 4, 2, and that produced diagonal movement. We just did it separately. That's fine. And if you want to do it again, let's again go for the next frame, go right 3, positive 3, go up 1, and that will bring you to, I don't know, what is that going to be? I guess 4 plus 3 is 7, so 7 on the x, And 2 plus 1 is 3, so 3 on the y. And that's diagonal. That's pretty neat, all right? Does that kind of make sense? You can represent it with another variable, an additional x offset in addition to the y one that we already had for the up and down limit. So it's like move a little bit in that direction, left and right direction, and move a little bit in the up and down direction. You can go anywhere you want, okay? We will also have to worry about the magnitude of things. I don't know if you guys have taken like a fancier math class, like this would be like a calculus 3 topic, sadly, but this direction and this direction, they're the same, right? But like the x offset and the y offset for this one versus this one are smaller versus bigger. Does that kind of make sense? So we would like to represent direction and not really speed. So like the longer the arrow means you're moving faster per frame. We just want to like always go in that direction somehow. So there's a way to like make sure the length of your arrow is a certain size, like make sure it's always of size 1. There's a way to go from any of these to like, all right, make it exactly length 1 meter, 1 inch or something. And that keeps you from like, all right, picking a random direction like this one versus this one. It's like slowly versus fast, okay? So there's a way to normalize your direction speed, okay? And that would involve changing one of these into like the same direction, keep the direction, but like change the offset amounts to keep the direction but make the length of that, the hypotenuse of the triangle 1, all right? So that's something we'll have to worry about later, but we'll get to that, okay? So I think that's most of it. So that's how we can represent directions with a change in x and a change in y. That will give us diagonal movement. Are there any questions about that? That's going to be pretty fun to program. It's going to look really cool. It'll be very, very satisfying next time. All right, the last piece of the puzzle is bouncing off those walls. All right, so we do know how to check for when we hit a wall, at least for the upper and lower walls. Something like this, like did we try to go outside? Did we try to exceed the bounds? And so that's going to work still. That's going to notice when we hit the top. That doesn't change. We're also going to need to worry about hitting the sides as well, though, right? The left and right walls. And we'll have to worry about bouncing off and like changing our direction because like that's not negative anymore. That's something different, okay? So let's figure that out, okay? So we're going to have to check the bounds of our turtle and bounce off those walls, okay? So what are our bounds, by the way? If we're going to keep what we had before, it was a 400 by 400 rectangle or square centered at 0, 0. There's 0, 0. And that means that, okay, this is going to be, that's 0, 0, and that's 400 by 400. This is y equals negative 200, and this would be y equals positive 200. Just cutting it in half. And then the x's would be similar. This would be x equals, this mark right here would be x equals negative 200, and this would be x equals positive 200. So we'll use those in our calculations. You will have to worry about like the width of the turtle because it's all relative to the center. Like, how do you know? Like, we're right here, we're moving. How do you know you hit this wall, you're exactly right here? How do you figure that out? It's always going to be based on the center point of our turtle, all right? Like, how do we know we're right there, just grazing that wall? Well, it's when the center point is exactly there, okay? So something involving like x being negative 200 offset a little bit by half the size of the turtle, like we were doing last time, okay? So that's going to be the game we have to play here. So, okay. If we forget about half the size for a second, it makes it easier to talk about, but we'll have to do that later, though. So yeah, for example, the turtle hits the left wall when the left side of the turtle, let's just pretend we can get that somehow, when the left side of the turtle, its x-coordinate is exactly negative 200, or a little less. Maybe we try to move it outside the bounds. We're moving too fast or something. That could happen. Okay, so that's when the turtle hits the left wall, when the x-coordinate becomes, or the left side at least, becomes exactly that, negative 200, or a little bit outside even, all right? If it tries to go less than that, we're going to rein it back in, okay? Same for the right wall, right? The x-coordinate of the right side of the turtle, if we're hitting just the right wall, exactly right there, is x equals 200, okay? That's what we need to worry about. Or try to go outside, like it's bigger than that, bigger than or equal to. So that's for the right wall. And then we know about the top and the bottom wall already, right? That was if the top part was like trying to go exactly equal to 200 in the y or bigger than 200 in the y. That was for the top part. So we've already done that. That was all this code right here. That was the bottom wall. This was the top wall, 200. And you also have to worry about the width, though. So that's what we need to do, all right, to notice. All right, now we've noticed. How do we change the direction now? Okay, because like we're coming in with, I don't know, let's say we're hitting the left wall, because I've already drawn that. Let's say we're hitting the left wall. Here is the left wall, zoomed in. Here is our box. And we hit there coming from with a direction like that. Like the direction that took us right there was this one of this delta x, that was negative, and this delta y, that was positive. It took us right there when we hit the wall, okay? We want to bounce off exactly in this direction, right? That would be correct, wouldn't it? Boop, boop, something like that. So you came in this way, you're going to bounce off that way. Or not to scale, though. Came in that way or bouncing off that way. Something accurate, right? But do you see that this triangle, this new direction triangle, looks a whole lot like the old direction triangle, doesn't it? That's going to be the secret. The geometric secret becomes you are still, like the triangle is exactly the same, it's just mirrored on an axis. So you are moving left, you're moving left and up. Now you need to move right and up, and you don't have to magically come up with anything new. It's your delta x was negative, make it positive, negate it. Now you were going left and up, go right and up. Keep the same delta y. That's going to give you the new direction. Does that kind of make sense? It's the same triangle. You're going that way. You need to go that way instead. So instead of going left, go right. And still go up, though. The y didn't need to change for the left wall. Are there any questions about that? Because that's going to be the secret to notice that. All right. Your old direction was this. Your new direction is based off of the old one. If you hit the left wall, it's like you don't want to go left anymore. You want to go right. But keep the same upward motion. And that will give you the exact correct new direction to bounce off that wall. You could make a random direction, but that would look a little weird, I would say. So like you could come in this way, hit the wall, and then bounce off, like back down that way or something. You could pick a random new direction, yes, and that would involve picking a new delta x and a new delta y. Yeah, and that you should try that once I code it up. You can make it bounce off in a weird way, but hopefully not towards the wall again. You'll have to be careful about that. Yeah. And the same thing is going to be true for the top and bottom wall. So I think you can imagine like the right wall is going to be very similar to this picture. The top and the bottom walls are also going to be similar. So let's say that we were coming in like this, and like here's my box. Hit the wall just like that, and we got to bounce it off. I don't know, in that way, whatever. Okay. So here's what you got to do. So if this was my old direction, I came in and I hit the top wall somehow. This was my delta x. It was positive. I was going right and up. Delta x was positive. Delta y was positive. I want to bounce off in that way. Yes? Which is going to be the same triangle. Where do I want to put that? I don't know. I don't even know. It's got to become that triangle, essentially. Coming up like that, I got to bounce off like that. That's my new direction. And it's very hard for me to draw this to scale. There. That looks like the right one, right? We're coming in that way, got to bounce off that way, which is going to be the same, right? Same delta x. It's the same triangle, really. But instead of moving right and up, it's going to be right and down. Okay? So it's the y that needs to be negated now. So the old delta y, we just negate that, and the new delta y is whatever that was. So go down and right now. And that gives you your new direction. That gives you your new bounced direction off of the top wall, and it's going to be the same for the bottom wall too, if you draw it. Okay? So the moral of this story is, all right, to get your new direction, if you hit the side wall, left or right, you're going to negate your x offset. So like you were going left, you hit the wall, it'll bounce you off right now to negate your x. Keep going up or down in the same way, though. And then it's going to be negate the y offset of your direction if you hit the top or the bottom walls. See, like you were going right and up, go right and down now. Keep going right, that's fine. But you were going up, you need to go down. Okay, and that's going to give you the new correct direction. Any questions about that? I'll draw a zoomed in picture with some actual example numbers, but that's going to be what we need. All right, that's going to give us my new direction that I need to bounce off in, and that's what we'll code up. All right, so okay, let's have a good worked through example with numbers this time. Let's say we've got our box right here, and its coordinate of its left side, for example, let's say, is negative 198, 2. Okay, and let's say that our direction is this. It's going to be move negative 2 in the x direction and up 3 in the y direction. All right, so we're moving this way, and this, right, in the next frame, we're going to hit the wall, aren't we? We're going to go right here, exactly hit the wall, because our new direction is going to be, right, we go over negative 2, right, and go up 3. Up 3. That will bring us to negative 200, and then, I guess, 5. So that's my new coordinate, negative 200 of the left side at least. Negative 205. So there's my left wall. We've hit the left wall, and we want to bounce off in exactly this way, right? Finally, I can draw it to scale. We want to go right here in the next frame. That's going to require changing our offset to be, it wasn't this anymore, right? It's going to be positive 2. Go to the right. Positive 2, stay positive 3. That's what needs to change. So we're going in this way. We need to bounce off and move this way. This is going to be our new direction. Positive 2, positive 3. And that will take us to, in the next round, now it's back to negative 198, I guess 8? Yeah. That's what we're going to have to worry about. All right, so that's an example worked through with numbers, and I hope that maybe helps. All right. Are there any questions about that? It's going to be, all right, we noticed that with like an if statement. We hit the wall, we were moving with our direction, delta x, delta y. And we're going to change our directions because we just hit the wall. We're going to bounce off in the opposite way. If it was a sidewall, we're negating our x direction. So negative 2 becomes positive 2. And that will give us the correct way to bounce off. Okay? So that's the secret. That's what you got to do. And try to code that before next time if you can. Be a great exercise. Start with what I gave you, with like the original bouncing, because there's no gravity in this example. But I think that is all that I wanted to say about bouncing squares for now. We'll code that up next time. All right. If we're good, that is most of the day. I just need to give you new stuff to work on. So here, time for a new essay and a new programming assignment. This essay is your last essay. There will be no more essays after this. You made it. You're almost to the end of the semester. So your very last essay, let's go out with a bang, and I'll just let you write about whatever you want to write about. All right, so this will be create your own essay. Here's your prompt. Build your own essay. Do whatever you want. Write about some topic that's relevant to the class, right? Related to computing technology or the internet, that interests you and has social or ethical implications. Something that is like useful to talk about in a critical thinking essay. The only thing you can't do is write about something I've already asked you to write about. All right, so just pick some other topic than other previous essays and go crazy. Okay, so you will have found some issue that's relevant, and go pick it apart. All right, talk about it however you need to. Like talk about the assumptions that are involved on both sides, like the people who are pro this thing, anti that thing. Talk about any fallacies that people are like they tend to use when they're arguing their points for this topic that you've chosen. Talk about Kant or Mill. That might help. I don't know. Whatever you'd like. Go crazy. But this is going to be a research paper essentially. All right, so you're going to write 1,000 words at least, and I want you to do some research. All right, this is a research essay, so go and find 4 works on the internet about this thing that you care about. All right, does that make sense? So very open-ended. You can talk about whatever you like to talk about as long as it's relevant, but go and do some research. It's going to take you finding some things, right, and citing some sources. All right, and I can help you find any sources if you're interested. But yeah, that's what I want. A 1,000-word essay on a topic of your choosing, as long as it's not similar to old essays and still relevant to the class. All right, we good with that? All right, last example, last new assignment. You're still going to have one more programming assignment. Let's just do week 16. So there's still a week left to give you another programming assignment. So you'll have one more after this one, but this is the second to last programming assignment. What I want you to do is make a Python program that is very similar to not the gravity example, but the one from last time. So like the old bounce. You can start with this old bounce. Where is that? The lecture 24, the one before this, that bounce program. So start with this one, this code that does like constant speed bouncing. And I want you to change it around in a fancy way. All right. So what we're going to do is you're going to take this code and you're going to modify it. So you're going to pretend that the ball is magical, and sorry, the ball is, I guess, the ball is normal, but the walls that it may hit are magical. All right, the top and bottom wall. So I want you to do the following: draw that bounding square, make an animated bouncing ball. I've already done those things. Steal my code, and then what I want you to do is I'm forcing you to add on to your wall bouncing code. All right, I'd like you to have the walls be magical and make something weird happen every time the ball hits one of those walls. All right, so hook into the code where we're noticing that the wall has been hit. That's these if statements, right? That's the bottom wall code, that's the top wall code, so add to the body there. And what you'll do is make something weird happen to the ball every time it hits one of the walls. Here's some things that you can do. So like you can change the color of the ball every time it hits the wall to something random. You can, or like you're going to pick from one of these random things. Like pick one of those random things to do each time you hit a wall. Like you can change the size of the ball by some offset. And there's something in the random library that lets you choose a float, a number that has decimals, a random number that's like within a range, called random.uniform instead of random.randint. Look into that. That might help for the changing the size of the ball. You can change the x coordinate to have it teleport when it hit the wall. That would work. You can change the speed of the ball. That's which variable? That was going to be our offset variable. That's the speed of the ball, how big that is. You can multiply it by something to make it faster, or divide it by something to make it slower. You can also change the shape of the turtle to be something other than a circle. Because we made it a circle, that was the ball, but turtle.shape, you can give it square, you can give it triangle, all those things, all right? So that's what I want you to do. I want you to hook in to when the turtle hit one of the walls and pick something random to do as if the walls were magical, all right? So your last real requirement is I want you to make a new function as well, all right? Make a function called do something weird or something like that, and I want you to call that, all right? I want you to call your function do something weird inside of this code where you hit a wall, okay? And that will pick some, like it'll flip a coin and it'll pick some random thing that it could possibly do, all right? So you'll call that every time the ball hits the wall, and what I want you to do is have at least 3 magical random things that could happen, all right? So don't just like only do color. Do at least 3 different weird things that could possibly happen every time the ball hits the wall, all right? So you do something weird, is like flip a 3-sided coin or roll a 3-sided die and like pick one of those, okay? At least, all right? So yeah, you can use a lot of my code, but that's kind of like the setup. I know there's a lot of words that I just said, so I've made a nice example. So here's a GIF of what you might do, all right? So here it is, like it's bouncing, like the speed has been changed, obviously. So here it is restarting. It's like, all right, hit a wall. Magically chose to change the shape, speed, color again, speed, shape, x direction, so it teleported, color, speed, size, so all those things. When the ball hit the wall, choose something random right then and like have it affect the ball. Does that make sense? It's like one thing each time, but like have 3 options at least that would be chosen. All right, so that's hopefully that example helps. All right, so yeah, as a hint to pick something random, because you're gonna have to like pick one of these random things to do each time. Here's a way to roll like a 5-sided die. If you have like 5 weird things to choose from, you'll pick a random number between 1 and 5. You know how to do that with the random library, and then just use a big long if-elif to do one or the other. So like if the number was 1, if the random number was randomly 1, do your first weird thing. Elif that random number happened to be 2, do your second weird thing. That's how you can choose from one of the 5, for example, or one of the 3, however many you make. Okay, so yeah, just like make a program that somehow looks like this, and that's pretty much what I'm looking for. All right, so there were a lot of words to get there though. Hopefully I've explained it enough, but that will be due in a couple weeks. Any questions about that one? Do yell at me if any questions come to you, but you can use a lot of my code, and I'm just forcing you to make your own function essentially, all right, and figure out how to call it. So I think that's all that I wanted to say for the day. Let's make sure. Just those 2 new assignments for our 1 lecture of the week, and yeah, that's all that I've got to record.